Okay. 7.3. Kind of a big deal for this unit, which is why everyone is here on time. Translation theorems, sorry, I don't know why I put translations. Translation theorems and derivatives of a transform. Those are the themes. Okay, and the reason this is so important, currently we don't have a very extensive list of Laplace transforms. So we either hope that it's one of the 5 functions that we're very comfortable with, or we have to use the definition, which is really annoying, right? We don't want to do that. So the goal here is to try to find things that we can do to try to get more Laplace transforms under our belts so that we can use them at any time. So given, let's say, the Laplace transform of f of t equal to some function. Now we're going to start translating some of those, so at least now we have more options. We can find the Laplace transform of any of those functions that we already know, including functions with a exponential factor within the function that we're also taking the transform of. And the way we do that is by translating our answer, f of s, to f of s minus a. So you see this same format for the transform of the function, but now wherever we saw an s earlier, now it's going to get replaced with s minus a. So we're going to go ahead and formalize what this is. It's actually called the first translation theorem, and we'll go ahead and prove it since it's not very difficult. Okay, so the first translation theorem is that if a is any real number, then the Laplace transform of e to the at f of t will be f of s minus a, where it's understood that f of s is simply the transform of f of t. So this is what I was saying earlier. As long as we understand the basic form of what the transform looks like, then it'll be relatively easy to translate it or find the result of our new function here. Okay, and here's the proof. So we start with what we know, and we don't know much except that we're trying to take the transform of e to the at f of t, so we'll just get right into it. So if we're trying to take the transform of e to the at f of t, the only thing that we can really use here is the definition, because we don't have really any other givens. So the definition would be to integrate from 0 to infinity. We have e to the minus st, and now instead of f of t, we put the entire function in the integrand. And now We're almost done. We can group these exponentials together. So it's e to the minus s minus a times t. So if I factor out a negative t, that's what we get. We still have our f of t dt. And now this looks exactly like the definition of the transform. The only difference is that instead of having e to the minus st, we have e to the minus s minus at. Does that make sense? So by definition, this is equal to f of s minus a. Because we know that e to the minus st is capital F of s, right? So e to the minus s minus a times t. F of t will be f of s minus a. And that's it. Pretty easy proof. Okay? So a couple of examples. Okay, so if we're trying to take the transform of e to the f, or e to the 4t times t squared, for the time being, we'll kind of ignore this exponential factor, and we'll just kind of work with t squared. The transform for t squared would be what? You guys remember? What is it? 2, well, I'll write it with the factorial, but yeah. 2 factorial, or 2 over s cubed. Right, it's always one more. And now, the notation, which you don't have to really do every time, but just so that we're clear, all we're going to do is translate s to what? S minus 4. So all that means is that our answer will be 2 factorial over not s cubed, but s minus 4 cubed. And we're done. Okay. One more. E to the minus pi t sine of 5t has what form? So ignore the exponential for a second. If we're transforming sine of 5t, what is that? So, and now instead of s, s plus pi. Very good. That's it. First translation theorem. Pretty easy to work with. This next one is the inverse version which we won't write out all the notation, but we'll just get right into it. If we're doing the inverse transform of some function and we recognize that it's been shifted or translated, then that'll simply be e to the at f of t.
Please excuse the interruption. Buses route 14 and 4 have arrived late. Please allow students to class over the next couple of minutes. Bus route 4 and bus route 14 were late today. Thank you.
I'm sure that's why you guys were all late, right? Okay. So here's the inverse form of the first translation theorem. It's not too bad to work with. If you recognize the form and you see, oh, that's a sine or that's a cosine, and it's been shifted, it's easy to do. If it doesn't quite look like it should and maybe you can make it, then that's the goal here. Let's say we have s over s squared plus 6s plus 11. Okay, so I mean right now, you can't factor that. You could do partial fraction decomposition if you want. It doesn't look like any of the transforms that we know about, right? If you complete the square, this might help. This is one of the techniques when you have a quadratic in the denominator and you're taking the inverse. So let's do that. S over s squared plus 6s plus 11. What does that look like? Well, this is the same as s over, if I complete the square here, this would be the same as what? S plus 3 squared plus 2. So far I haven't changed it at all. And now it's starting to look a little better. This kind of indicates that it's been translated, right? The plus 3. We really wish, what? That not only we had an s plus 3 here, but where else? On top. So let's do it. Let's just put it there. You can't just do that. So how do we fix it? Yep. And now we know how to do the transform of each of these, right? So if we're taking the transform, the inverse transform, of s plus 3 over s plus 3 squared plus 2, plus the inverse transform of negative 3 over s plus 3 squared plus 2. This looks like s squared, and 2, right? So what function is that? Cosine. So it's going to be cosine of what? Root 2 times t. Now, since we have been shifted a little bit, what else do we put in front? E to the negative 3t. So there's the cosine term. Next, if there's no s on top, but we got the same denominator, that's what function? Sine. It's negative, so we'll do minus. Now we do have to adjust this a little bit, right? In order for it to be sine, what we really wish we had up here is the square root of 2, right? Because it's the constant and then the constant squared on bottom. So we would have to divide by root 2, and we still have our 3 there, and then everything else is the same. So once you get a little bit more comfortable with this completing the square technique, well, if you don't like partial fractions, now you have another option. Okay? Any questions on that? What time does this class end? Is that our time or the normal time? Normal time. So I have until 47? All right. Questions? We good? Okay. Before we go on to the second translation theorem and the derivative piece, talk about the unit step function real quick, which is essential background for the second translation theorem. And it's defined like this. We have a u of t minus a. Whenever you see this fancy notation, we are referring to the unit step function. And all it is two things. It's either 0 or 1. It's kind of like an on-off switch. Okay? 0 means it's off. 1 means that it's on. Does that make sense? And this a value indicates where that where the switch gets turned on. So we're going to say it's off from 0 from 0 to a, and then starting at a, that's when we turn this guy on. You think we could have a pen? Yeah. Yep. Thank you. So we're only going to deal with positive time values here, and 1 just indicates that after a certain amount of time, we switch everything on. So whether that's some external function that's acting on our system, or whatever the case is, that's the point at which things actually start working. So. And I know you guys can graph it, but might as well put it here. So from 0 to a, we're off, starting at a, and forever, we are on. So this is what the graph looks like. So naturally, if you had something like this, what does this mean? What does this look like? Yeah, so the only difference is now we actually have a value. So at t equals 4, that's when we have a value of 1. Before that, it's always 0, right? So no different. Okay. And now here's really where we start to see why this is useful. When a function is multiplied by this unit step function, that's exactly what it does is, we have a function that we're interested in, but we don't really want that function maybe until a certain point. So what it does is it keeps it off until we want it to come back on. So it turns off part of the graph. And this should be a pretty intuitive thing. So if we did an example and we defined f of t as cosine t times u of t minus pi without having to actually like go through the whole, here are the two separate pieces, all this means is that cosine doesn't get turned on until when? Until pi. So until pi, we got nothing. So from 0 to pi, we don't have any cosine graph yet. It's just 0. But now, starting at pi, we pick up our cosine graph wherever it would have been, right? So where's cosine at pi? What? At -1. And then at 3 pi over 2. And 2 pi. I mean, you know what it looks like. So after that, it does what it should. Okay. This kind of makes sense, this whole turning functions on and off thing. Okay. Now here's the other benefit of this unit step function definition. This allows us to take regular piecewise defined graphs and then write it in compact form. So instead of having, here's a function f of t and it's got 2 or 3 different pieces to it, now we can write it as, here's this function, one line, and then we just have to mess around with when things come on, when things shut off. But so for example, if f of t is defined as some function g of t from 0 to a, and then some other function h of t from t to a, or I'm sorry, from a to infinity, here's what we can do. To write it in compact notation or in compact form, we're assuming we're only from 0 to infinity, by the way. So what do we start with at 0? G of t. But now, at g of t, or I'm sorry, at a, what do we want to do? We want to go h. So two things need to happen. One, we need to throw h into the mix now, right? Two, we need to somehow shut off g of t. Okay, so how do we shut off g of t? Let's do that first. We could subtract g of t, but then we don't want to subtract g of t starting at a, because then that would throw things off, right? So what do we multiply it with? 0, which means we want u of t minus a. Does that make sense? So right now, if I just looked at this notation, this means that, well, this part means I have 0 up until a, right? 0 up until a. That's why the g of t is here. So now really what I have is g of t. Does that make sense? But now, as soon as I hit a, this guy gets turned on, so I still have g of t, but now I'm subtracting g of t, so I have nothing, right? So now what do I do to get to h of t? We just add h. And we don't want h to be on at all until a, so there it is. Okay. That's kind of the intuitive way of doing it. Now, if you don't believe that this works, I mean, you could verify it using the definitions. If we take g of t Well, we have two pieces, right? From 0 to a, and then from a to infinity. So if I have g of t minus g of t, according to the definition, what does u equal from 0 to a? 0 plus, here's h, and again, we have u, which equals 0 from 0 to a, right? So you guys see that that works. This is 0, that's 0, so we have only g of t from 0 to a, which is what we wanted in the first place. And now if I look from a on towards infinity, we have g of t minus g of t, and then what's u? Starting at a. 1. And then we have h of t times 1 again. So now g of t cancels out, and we get just h of t, which is what we wanted. Okay?
I got a question.
Yes?
Why? So, u of t, when I say that's defined in terms of a piecewise function, why wouldn't we just, what would be the advantage of doing it that way instead of just making g of t and h of t a piecewise function and stop?
The advantage of doing it like this is when we start working with differential equations, we want to have things in a condensed form. This is to save space, but also the second translation theorem is directly related to the unit step function. So if you can have a piecewise defined function, whether it's 2, 3, or 4 different pieces at one time, and somehow write it in compact form, you can go straight to the second translation theorem and start solving the differential equation, instead of having to do like 4 separate solutions. Does that make sense?
Yeah.
Okay. So I mean, yeah, it's really just save space, and it'll make things a little more compact for us. Okay. Anything else? Okay. Let's try, just to get used to the notation. Let's say f of t is equal to 0 from 0 to a, g of t from a to b, and then 0 again from b towards infinity. So this would indicate flipping the on switch for just the finite amount of time, and then we shut things back down, right? Shut it off. If we condense this in compact form, this would be f of t equal to what? What do you guys think? What do we want first? We don't want anything, right? So we're okay. What gets turned on? G of t, when? At u of t minus a. But now we want to shut it off, so we're going to have to subtract g of t at u of t minus b. That's it. Okay. Here's an example to try real quick before you guys get out of here. Let's say we have e of t, so maybe this is like an LRC circuit, equal to 20t for 0 to 5, and then shuts off after 5. How would I write this in compact form?
20t minus 20t u of t minus 5.
Yep.
Plus, what should I say?
It'd be plus 0, but yeah, we don't need that. So we have 0 and then u of t minus 5 if we want to keep that idea, but we don't need it because that'll go away. Does this make sense? Okay. So all that you need to do today, or have gotten from this, is first translation theorem, which isn't too bad to work with, how to go back the other way if need be, and then getting comfortable with the unit step function notation and how to rewrite functions using it. And that's it. Okay, tomorrow we'll finish the section and we'll go through the second translation theorem and the derivatives of transforms.